Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Energy Storage Systems, Silicon Carbide, Multi-Modular Approach, and BMS Tackle the Latest Trends. Brought to you by Tech Online, Infineon, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event, and you may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window, and then click the Submit button. Please note that we'll try to get to as many questions as we can in the time that we have left at the end of today's program. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. Also at this time, we recommend that you disable your computer's pop-up blockers, and at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation. Energy Storage Systems, Silicon Carbide, Multi-Modular Approach, and BMS Tackle the Latest Trends. Discussing today's topic are Nenad Balancic, Global Application Marketing Manager, Infineon Technologies, Austria AG. Nenad holds a business degree with specialization in international business and management from the University of Southern Denmark. And joining him today is Damian Zupancic, Applications Engineer, Infineon Technologies, Austria AG. Damian joined Infineon in March of 2015 in the AC/DC Application Engineering team, which is involved in development of HV power switches in range 400 to 1,000 volts, where he is responsible for the concept engineering of 650-volt silicon carbide diodes. And finally, Peter Green, Application Engineer, Infineon Technologies, Americas Corp. Peter is the manager of a product and system application engineering team supporting renewable energy systems and low-power motor drives in Infineon PSS Business Unit, DC-DC Division. It's with great pleasure I now turn this special session over to Nenad to begin. Nenad, take it away.
So let's start with the introduction of today's webinar. As you can see, energy storage systems, or short abbreviated as ESS, has a wide range of where it can be applied and what purposes it fulfills. And to clear out the way for this webinar, there are many sorts of energy storage systems we see, especially hydro, flywheels, and so on. But for today's webinar on energy storage systems, we will focus on battery energy storage systems. As you can see on these slides, usually there's a split of before the meter and behind the meter. Before the meter is usually linked to high power systems, either in combination with PV, so photovoltaic utility scale systems or wind systems in the generation phase, or also in the transmission phase, where you have to transmit this energy from point A to point B. This is also called behind the meter. Looking on the right-hand side on the purple area, which will be also more the focus of today's webinar, is the behind the meter. So everything that is behind the meter is tagged here, and here we see especially commercial, residential photovoltaic systems in combination with energy storage system playing a key role, but also charging stations, for example, for EVs, are falling into this category. So as I just mentioned in the previous slides, in this webinar, we're looking at the behind the meter. But please consider that some aspects, for example, that will be discussed later in the BMS section, are also applied before the meter. Now, looking into energy storage systems in combination with rooftop photovoltaic system, we clearly see several trends why energy storage is becoming a hot topic in this area. First of all, consumers or households are want to reduce the consumption from the grid, so making them also increasingly independent from the grid, especially in areas, for example, where natural hazards are increasing, where you have bushfires, for example, in California, or also other areas. If you live on the island, you want to have energy also when the grid goes down. And as you can see in the slides or in the graphs below, on the left, on the right-hand side, is an average power consumption of a household, where you can see that clearly everything that is installed or has installed solar systems on the rooftop, you can just use this energy when you have sun. So during the day, you have no problem. But what to do with the power that you harvest during the day excessively, so you cannot use it during the day, but you want to use it at night. So one of the solutions here is clearly energy storage systems. The same thing applies for commercial and smaller utility solar systems. A lot of things are in common here with the residential photovoltaic systems. We see that the commercial installations fulfill also tasks of storing this excessive energy from these fields during day and to use it later on, especially during night. But also what we see is that frequency regulations of the grids are now playing a major role, because more and more battery-powered or battery-driven applications are entering the market, and people are more dependent on things that are cordless. So we see a higher demand here for energy. So to peak shave also this energy demands throughout the day, for example, in the morning when you need more energy, or at night when it's getting darker, energy should be stored in batteries and released throughout the day or throughout the night when it is needed. Also, what is a hot topic here, and we will discuss in one of the sections of my colleague Peter, is kind of the second life of batteries, which is also in the sort of containers, what you can see on the right side on the bottom of this slide, where batteries of EVs can be used in a commercial or utility scale, and not just to recycle them, but you can really reuse this battery and have economic use of such batteries in the future. Now coming to a short overview of the energy storage system markets and the outlook throughout the next years. So looking at the top graph, you can clearly see that the demand throughout the globe, or the installations throughout the globe for energy storage systems, will increase. So just giving you an assumption or an indication of the market throughout the next years, where we see that now, or 2 years back, we had about 2 gigawatt of installations. This figure will 5 times increase over the next 5 years, leading it to a CAGR of 22%. And what you can also see from this graph is that the US is the major market, or the major area where energy storage will be pushed on the installation side. There are several reasons. First of all, certainly the need to convert to green energy, and also the push from the government side to deploy such sources of energy. But one of the major roles as well is the price of the batteries, which we have seen just in the past few years even decrease by 100%, and it's predicted to even lower the price of batteries throughout the next year. So this is also a main game changer in deploying energy storage systems, that households and also utilities are taking energy storage or battery energy storage systems as a source to store energy. Looking at the bottom graph, there's a split of where this energy storage is located. And residential, according to IHS figures, and please consider these figures are before the COVID impact we see this year, but we don't see such a huge impact on energy storage systems for the next years, because it was anyway in the infant stages of deployment. But we can clearly see that residential has the highest CAGR throughout the next years, followed by front of the meter, which is usually a synonym for utility scale. And the reason, again, is for this residential increase is this PV systems in households are widely deployed, and then customers also want to use this energy, as mentioned before, during other days of time where they cannot harvest the sun to energy. So they want to have a storage backup systems to use this energy later. Secondly, as I said, the batteries are getting cheaper, and households and consumers, which are, let's say, even more impacted by the price of batteries, are also willing to pay for a battery if it's in a reasonable price, and incentives throughout the globe are also pushing heavily in this direction, why we're also seeing that energy storage system will be a topic for the next years. So saying that, we from Infineon, we see a lot of trending topics for these energy storage systems, and what you can see on this slide is certainly three main trends that are now going to happen and are also going to shape how energy storage systems will look like and what will be the driving forces for also system solutions. So one of them, which will be silicon carbide, so basically SiC in energy storage systems, which my colleague Damian will cover in a second. The second thing, main big thing is the second life of batteries. We see now a huge increase in EVs, which will be even more throughout the next years. So here a solution how to reuse these batteries in a good and economic way will certainly be of a hot topic in the next years. And finalizing on the BMS side, so BMS stands for Battery Management Systems. We see that more and more the batteries are deployed, especially in lithium-ion. So we need to guarantee that these batteries are safe and don't expose any risk to the end users. And here the Battery Management System plays a key role how this can be achieved. So saying that, I would like to hand over to my colleague Damian to cover the first trend, which is silicon carbide in energy storage systems. Damian, please go ahead.
Okay, thank you, Nenad. So in general, any energy storage system consists of two possible coupling systems, which usually comes along with PV installation. Those can be either AC coupled system or DC coupled. AC coupled system can be installed after PV installation or even standalone. On the other hand, DC coupled system enables more compact solution with hybrid converter combining MPPT stage for a PV and bidirectional DC-DC converter controlling the power flow in energy storage system. Furthermore, DC coupled system requires only one DC-AC inverter. An advanced residential and commercial energy storage system contains of lithium-ion battery, which requires its management system. Peter will discuss later more about BMS. Let's continue with power conversion. So in AC coupled ESS, the first stage of the power converter is an AC to DC. In a single phase setup can be seen topologies such as NPC2, ANPC and CCM totem pole PFC, where the first two can achieve higher power. So in NPC2 topology, a conventional solution uses 1200 volt IGBTs for fast switches Q1 and Q2 and 650 volt IGBTs for slow switches S1 and S2, both compact with fast recovery silicon diodes. A quick step to improve the efficiency of NPC2 is to replace Q1 and Q2 with silicon carbide MOSFET like CoolSiC and switches S1 and S2 by fast body diode MOSFETs like CoolMOS CFD7. A next step to more compact design is an ANPC topology where switches S1, S2, S3 and S4 operates the line frequency while Q1 and Q2 modulate at 50 kHz and could be even more with the silicon carbide MOSFETs. In ANPC, all power switches can be rated 600 or 650 volt breakdown voltage, what benefits in a BOM cost. Furthermore, high switching frequency and using silicon carbide switches allow to increase efficiency and power density at the same time. And the third topology, continuous conduction mode totem pole PFC, is a novel topology enabled by wide bandgap power semiconductors such as silicon carbide. The topology requires for fast switches Q1 and Q2 wide bandgap power switch, and therefore 650 volt cool-SiC is the right fit. As slow switches S1 and S2 operate at the line frequency, therefore CoolMOS CFD7 would be the right solution. In the three-phase setup, in an AC to DC stage could be used again ANPC2 or ANPC topologies, where the system is expanded with two more legs using the same power switches. Again, ANPC2 and ANPC can enable higher power, while B6 could be used at the lower power levels due to simplicity. B6 requires only 6 power switches, which has to be 1200 volt due to the 800 volt DC link voltage. A conventional B6 setup is realized with IGBTs such as 1200 volt H3, while with cool-SiC MOSFET higher efficiency as well higher power density can be achieved. So therefore, Infineon would recommend the 1200 volt cool-SiC MOSFETs. In order to properly control the battery voltage, a DC to DC converter is implemented in energy storage system. In residential as well commercial system, galvanic isolation is done in DC stage, where 3 topologies were identified. On the primary side, the selection of power switch depends on the DC link voltage fixed by the topology used in AC to DC stage shown in previous slides. In ZVS, phase shift full bridge topology are recommended in a setup with 400 volt DC link, either 600 or 650 volt CoolMOS CFD7 and 650 volt cool-SiC, which enables even higher efficiency. Furthermore, 650 volt cool-SiC diodes are the right choice for D1 and D2 diodes on the primary side. In the DC link, if the DC link is 800 volt, then 1200 volt cool-SiC MOSFETs and diodes can be used. On the secondary side, for switches Q5 to Q8, the selection of power switches depends on the battery voltage. In residential ESS, there are often used 48 volt battery packs, while in commercial segment is more in domain of 400 volt batteries. If the battery voltage is below 200 volts, then the Optimos switches can be used. So if the battery voltage is from 200 to 400 volts, then 600 or 650 volt CoolMOS CFD7 or 650 cool-SiC are the right choice. It applies a similar selection criteria for dual active bridge and CLSC topologies, with a difference that dual active bridge and CLSC don't require 2 diodes on the primary side. I would like to give some insights in silicon carbide material. What are differences and benefits in comparison to standard silicon power switches? Silicon carbide is called a wide bandgap material. Beyond that, it enables significantly higher breakdown field and improves thermal conductivity. Higher operating voltage, higher switching frequency, and better thermal dissipation are possible thanks to better thermal characteristics of silicon carbide technology. I would like to show the conduction loss comparison of 3 best-in-class Infineon's power devices, including 650 volt IGBT, IKW 30N65H5, 600 volt superjunction MOSFET, IPW 60R031CFT7, and 650 volt silicon carbide MOSFET, IMW 65R027M1H, at a junction temperature of 25 degrees C, what is often a datasheet condition, and 125 degrees C, which is a more applicable value. The comparison includes 8, 16, and 24 amps on-state current, where in all conditions 15 volts were applied on the gate. Firstly, it can be seen the conduction losses of IGBT are significantly higher than of other devices at 25 degrees C. However, it doesn't rise significantly the conduction loss for IGBT with a higher junction temperature. Secondly, the conduction loss of the superjunction MOSFET at 125 degrees C is 2 times higher than at 25 degrees C for the same device. Thirdly, looking at the data of silicon carbide MOSFETs, it shows only approximately 20% of conduction loss increase over the temperature range. This makes a clear difference between silicon and silicon carbide MOSFET technologies, especially at high current and high temperature operation conditions. So in the following slide, I would like to show you conduction loss comparison based on different applied voltages on the gate. So typical driving voltage for an IGBT, it's 15 volts. Therefore, the lowest line shows the RDS on of silicon carbide MOSFET applying 15 volts gate to source voltage. So if we only increase from 15 to 18 volts, so there could be achieved a gain in RDS on of 18%. So additionally, Infineon doesn't recommend any negative voltage for turn off, what simplifies the driving of the MOSFET. So we are going to compare Infineon's best-in-class technologies, trends top 5 IGBT, CoolMOS CFD7 superjunction MOSFET with fast body diode, and cool SiC silicon carbide MOSFET with focus on switching losses. In a setup with IGBT would bring already 30% loss reduction, replacing silicon with silicon carbide diode, thanks to reduction in the reverse recovery. However, up to 80% improvement of the switching performance could be achieved by replacing IGBT with silicon carbide MOSFET due to significantly lower diode recovery losses and turn-off losses. In addition, SiC MOSFET does not require any more co-packing of the diode, since it has a body diode. On the right side, we see a comparison of 600-650 volt CoolMOS CFD7, a fast diode superjunction MOSFET with a silicon carbide MOSFET. CoolSiC MOSFET shows a significantly improved QSS, gate charge, and it has 10 times lower reverse recovery charge compared to CoolMOS CFD7. The reverse recovery charge is one of the most important parameters for any resonant topology or any topology which is having a continuous hard commutation on a conducting body diode. Such topology is the CCM totem pole PFC, which will be shortly described later on. The QRR is the charge which needs to be removed from the body diode after it's conducting. So Kulmos has already found ways in order to reduce reverse recovery charge of the body diode, which came out as a fast diode device, Kulmos CFD7. Nevertheless, this charge was still too high in order to achieve high efficiency values in the CCM totem pole PFC, but now the CoolSiC comes into place. CoolSiC has once again 10 times lower reverse recovery charge than the best in class superjunction MOSFET available in the market. For any resonant topology, the lowest QRR results in additional robustness in hard commutation events, like it is a case, for example, in an LLC converter, which might enter in unwanted capacitive mode during some transient conditions, what would cause a hard commutation on the conducting body diode. As mentioned before, silicon carbide MOSFET enables a novel topologies which can achieve a superior efficiency. I'm showing Infineon's demo board 3.3 kilowatt CCM totem pole PFC, which achieves 99% efficiency and 72 watt per cubic inch power density. The board uses two CoolSiC MOSFETs, IMZ-A65RO48M1H in a fast switching leg and two Kulmos MOSFETs in a slow switching leg. All four MOSFETs are driven with two-channel gate driver and all are controlled by XMC controller. The board has auxiliary power supply with an Infineon flyback controller and Kulmos MOSFET in the flyback. I would like to show you efficiency comparison of the three different CoolSiC MOSFETs with different RDS zones, all used in the same operation conditions in 3.3 kilowatt CCM totem pole PFC demo board. So a granular portfolio of Infineon's CoolSiC MOSFETs allows to optimize the application and achieve optimal price-performance ratio. As a general rule, higher RDS zone tends to have a lower price. However, a device with lower RDS zone improves efficiency at higher output power due to the lower conduction losses and better RTH. So finally, let's have a look in the value proposition of silicon carbide in energy storage power conversion. In general, we see several challenges as well as requirements. First one is improved system efficiency. So the CoolSiC could potentially double the power density compared to a standard silicon solution like an IGBT with increased switching frequency. Secondly, a smaller size and weight reduction leading to higher power density could be achieved by the loss reduction, especially with the reduced switching losses, what would increase the efficiency, and then this would reduce the cooling requirement and would enable using smaller heatsink. Thirdly, bidirectionality and reliability. So with silicon carbide, higher robustness and better system reliability can be achieved. And the last point, cost reduction, could be achieved with the overall system cost reduction. So the higher switching frequency enables smaller transformers and inductors, and this would lead at the end that the same power could fit in a smaller box size. So that would be all from my side, and I would hand over at that point to Peter.
Thank you, Damien. Hello, everyone. It's great to be here. Now I'm going to speak a little bit about multi-modular approach to second life of battery. Now I'm going to speak about multi-modular approach for second life usage of batteries. In the next few years, we expect to see a rapid increase in the reuse of batteries removed from electric vehicles, EV. This is usually the case when the EV battery performance falls to 80% of its initial capacity. By 2030, 1 terawatt-hour of EV batteries will be available on the market to be reused in energy storage systems. Although used electrical vehicle battery packs may be recycled, it can be more economical to reuse these batteries that no longer fulfill the requirements of electric vehicles. Reuse of batteries, for example, in energy storage systems, is referred to as battery second life. Expensive testing, analysis, and matching of batteries, however, could diminish the economic advantages of the second life approach. The next slide explains the challenges involved. Challenges that come along with the used batteries include inconsistent characteristics of battery cells, different brands, different types such as cell pouch or prismatic, and different states of charge, SOC. The weakest cell determines the usable capacity of the system if used in a traditional system in which battery packs are connected in series. Regular maintenance is required, which involves temporary shutdown if one battery cell fails. Challenges that come along with traditional converters include a bulky centralized inverter with risk of a single point failure, high voltage operation that comes along with higher safety risk, a low frequency operation needing large and expensive filter components, and energy wastage due to the efficiency limitations of conventional inverters. Multi-modular cascaded multi-level architectures enable the use of mismatched batteries. Each module contains a battery pack and bidirectional DC-DC converter to individually control the charge and discharge. Faulty battery packs can be bypassed without compromising system operation. The major advantage of this approach is that batteries with different capacity levels may be combined without being limited by the weakest battery pack. The modules are connected in series and controlled by a master via a communication bus. The module outputs are combined to produce a high voltage, approximately sinusoidal full-wave rectified bus voltage. The output stage is a low-frequency unfolding bridge to create an AC sine wave output. The MOSFETs used are in the 100 to 150 volt range, requiring rugged, low RDS-on, with several devices connected in parallel. Infineon Optimos devices are ideally suited for this application, offering the market's lowest RDS-on as well as excellent thermal performance. Power packages such as TOL and D-squared pack are capable of carrying high currents required for this application. Infineon is already partnered with these two emerging companies who are both producing utility-scale modular cascaded energy storage systems. That is Stabil and Mobius. Stabil is located in Europe and Mobius in China. The next section is on battery management systems. To give a brief introduction to the battery management systems used in energy storage systems, a battery cell specification includes cell voltage, capacity, chemistry, and the number of cells in a module, which are the key factors for designing the battery management system. Battery management system performs the following functions. 1. Cell monitoring and balancing, CMB. This includes measuring temperature and battery pack current and determining the state of charge and state of health. Those are abbreviated as SOC and SOH. 2. Protection unit, for protecting the battery pack or rack against overcharge, excessive discharge, high temperature, and short circuits. Number 3. Battery monitoring and control. This is an interface between the central monitoring unit, CMU, and individual modules. Battery management systems in any application can be divided into 3 parts: cell monitoring and balancing, unit protection, unit battery monitoring and controlling unit. In systems containing a large number of battery modules, an isolated communication bus is included to allow modules to communicate with a central controller. A complete battery management system for an energy storage system is shown in the block diagram here. This consists of a battery pack containing the BMS, which monitors the cell voltages and temperature, which carries out cell balancing by removing excess charge from overcharged cells and also sensing when cells are discharged to their minimal level. The voltage and current for the whole battery pack is also monitored. All of this information is communicated to the battery monitoring and control unit, which monitors the battery pack state of health and also controls the battery protection unit. The BPU includes inrush current limiting and bypass switch control, necessary for safe connection and disconnection of the pack, and also to disconnect in the event of a short circuit or other fault condition. Battery protection can be implemented with a high current bidirectional switch, which can be formed with 2 suitable MOSFETs connected either source to source or drain to drain. The protection switch may be located either at the positive high side or the negative low side. MOSFETs for this task require low RDS on, low junction to ambient thermal resistance, a wide safe operating area, SOA, and rugged linear mode operation. Infineon offers several package options depending on the current carrying requirement, including high current capable D2 pack 7-pin and TO leadless, or TOL. When initially connecting a battery to a load with large input capacitors, there is an inrush of current as these capacitors charge up and the battery voltage to the battery voltage. With large batteries having a low source resistance and heavy loads, having large capacitors across the input, the inrush current can peak to 1000 amps. A pre-charge circuit is therefore required to limit the inrush current between the battery and its load. The pre-charge circuit initially connects the battery to the load through a resistor to limit the inrush current. A smaller MOSFET is used to connect the pre-charge resistor. This can be either N-channel or P-channel. Infineon offers these devices and packages shown here in the slide for this purpose. BMS cell balancing and monitoring. The TLE9012 is a 12-channel cell monitoring and balancing controller with 5 temperature monitoring channels. It contains internal cell balancing switches rated at 150 milliamps maximum current to digital conversion with accuracy of 12 bits, isolated and non-isolated UART communication interfaces, and standby current is as low as 3 microamps. UART interface. The TLE9015 is a battery management transceiver IC with 2 UART ports for communication to a host microcontroller. It includes the following features: 2 isolated UART ports for daisy chain communication inside the battery pack, CRC check for communication integrity, high robustness against external noise, 2 external fault inputs with internal latching, an error output pin to trigger external microcontroller error subroutine to react to any fault and shut down systems as needed, and internal supply monitoring and the low energy sleep mode. A complete battery management system block diagram is shown here based on Infineon controllers. TLE9012 monitors each battery module, and TLE9015 monitors the communication interface between each monitoring IC and the host microcontroller. This includes functions such as cell balancing, where this includes integrated balancing switch, balancing diagnosis, balancing time targets, and external balancing switches. Accurate voltage measurement with the synchronicity, 12 times delta sigma analog to digital converters, voltage measurement diagnosis, the additional block voltage measurement and comparator to ensure possible errors in the voltage measurement are detected, accuracy of plus and minus 5 millivolts, guaranteed by using a stress sensor and advanced temperature compensation, and filtering with several filtering modes ensuring that undesired noise can be eliminated from the measurements without influencing the system cost by needing to add extra components. Temperature measurement, including adaptive current selection for NTC. NTC current is provided and automatically selected by the device depending on the temperature value to maximize accuracy over the full range. And automatic measurement, temperature will be measured automatically by the IC without further triggering from the microcontroller to minimize communication traffic on the bus. Host communication. This includes UART-based communication. Isolated UART is based on UART frames that are transferred, including an 8-bit CRC to ensure data integrity until a microcontroller registers it. A high number of slaves. Communication allows up to 62 slaves without loss of signal. Ring mode topology is supported to ensure in case of one slave wire is, this solves issues in case of a slave wire failure. Power balanced. Each message will be sent over the full chain independent of the position of the receiver slave. Answers are also sent in both directions. Additionally, there is a master on top or bottom selectable without lengthy configuration, bidirectional communication scheme using error management logic, and capacitive isolation, which reduces space and cost of design. To summarize, the battery management systems for standalone battery packs and battery modules used within a large rack system have some differences as illustrated in the block diagrams. Communication with the central controller plays a very important role in larger systems, whereas standalone systems provide monitoring data only. Small MOSFETs are used for charge balancing. Infineon offers several suitable small package options. And with that, I'll hand back over to Ninad.
Thank you, Peter, and thank you, Damian, for your support here in introducing the trends for the silicon carbide for second life of battery multi-modular approach and for battery management systems. And I would just like to sum up and give you a short summary of the topics that we have just heard throughout this webinar. So the main three topics that we have discussed are silicon carbide in energy storage systems, multi-modular approach enabling second life of batteries, and battery management system BMS. So looking at the first one of silicon carbide, we will see that this trend will certainly shape how systems are designed. Because first of all, what you can achieve with deploying silicon carbide technologies in comparison to traditional IGBT technologies or superjunction technologies is you can achieve simpler bidirectional topologies, and the design effort is much lower than you have to implement with traditional topologies. Secondly, one of the main benefits is you can reduce significantly the size of your systems and also the weights. So higher switching frequencies enabled by silicon carbide are reducing the magnetics, and also the loss on the conduction and the switching is lower, so the heat sink efforts and the heat sinks can be reduced. And this in the end leads to a lower bill of material. So in the end you have a lower dollar per watt for the systems. And one thing that is really important is that silicon carbide is a robust technology, and dealing with energy storage systems, you have to have really reliable systems. So this is also a key feature of silicon carbide, that especially with increasing temperatures, as some batteries might stand not in the house but outside, can be exposed to higher temperatures. So higher system reliability is certainly a feature that when designing such a system has to be taken care of. The second big topic was the multi-modular approach. Why this is a trend, or might be a trend in the future, is simply explained, we will have a lot of EV batteries coming to the market in the next years from the unused or from the old batteries that cannot be any more used from the EVs. So one of these approaches is basically to have a multi-modular approach, so splitting the power instead of having a big inverter, which you have in a traditional designs, but putting a DC-DC or DC-AC converter on each of these battery packs that you have from the car. And one of the main advantages is that you don't have to sort these batteries. So you don't have to sort the batteries for the same voltage, you don't have to sort them for the same characteristics, and you don't have to sort them for the same state of charge. So this is enabling also a flexible design, and also it's more controllable, and you can draw basically each battery simply, and not one battery is influencing the whole system. And we have finalized this webinar with the battery management systems, BMS, because we see that these batteries, they have to operate, first of all, safe, but also to ensure, let's say, economic value, also efficient. So in order to ensure efficient and a long lifetime of batteries, a sophisticated BMS, battery management systems, has to be deployed. So what does this do? It fulfills two main functions for the battery, especially when dealing with lithium-ion batteries. First of all, it protects the battery, and secondly, it's monitoring the battery. What we mean by protection is it protects it when you charge it or when you discharge it, so not to overcharge it or not to damage it with some inrush current that can happen when you charge a battery, or also not to undercharge it, which is significantly reducing the lifetime of batteries and reducing the life cycles, or the cycles that you can charge and discharge, and in the end also reducing the economic effect. You can use these batteries as you have intended. So saying that, with these three main trends, silicon carbide, multi-modular approach, and BMS, we are certain that these trends will shape the energy storage in the next time and in the next years. And I would also like to thank Damian and Peter for elaborating on this more. And now I would like to hand over to Chris to check on the incoming questions, and happy to answer the questions with the team. So we are open now for incoming questions, and handing over to Chris.
All right, thank you, speakers, for a great presentation. We're now going to move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen, and then click the Submit button. Please note that we'll try to get to as many questions as we can in the time we have left. If we're unable to get to your individual question today, someone will get back to you after the program is over. And also, as a reminder, please fill out the feedback form that will open up at the end of the show. Thank you in advance for filling out the feedback form. Your participation in this survey will allow us to better serve you on future webinars. So let's get on with some questions here. We've got several coming in. Our first one here for you, gentlemen. Are you familiar with the architectures for second life applications in DC rather than AC grid? Or are the connections of the modules, I should say, or do the connections of the modules need to be in AC rather than DC?
Okay, Chris, I can take this. Nenad here. So yeah, it's a good question. But to start off with this one, this is rather a new approach, I would say, throughout the whole globe that we see that this is happening at the moment. There is nothing to speak against that you connect them to the DC, but since usually we see this most likely will happen in the utility scale of second life of batteries, where the grid is also in the AC, what you do is, of course, the batteries are DC, but usually you put on each module a power conversion, which you do at DC-DC, and then sometimes you can do it, as some of our partners is doing, having a big inverter to unfold it to AC. Or another approach is to directly have a DC to AC on module level and then splitting this and putting it into the grid. But frankly speaking, there speaks nothing against that you also make the same AC connection to a DC. You just need to have then a DC grid that put it in. For example, in residentials, let's say in a few years, if you can use this, or small commercials, which is maybe DC driven, you could use it also in the DC. I hope this answers the question. Back to you, Chris.
All right. Thank you, Nenad. We'll move on to another question here that says, do you recommend no negative gate voltage even when you drive the gate with 15 volts? And what's so critical about that?
Okay, Damian speaking. So in general, Infineon recommends zero voltage gate driving during the turn on, because we tune the device in the way that it's less prone to unwanted return on effects. And in addition, we also enabled higher threshold voltage. So it's typically 4.5 volts. So on that way, we were able to find a way to enable 0 volt driving during turn on. And also this at the end simplifies the design of the driving scheme. And in general, it's not critical to drive with negative, and it at the end simplifies the design. So thank you. That's from answer from my side. I hope that I answered the question.
Thank you, Damian. We'll move on to another question here. How is an inverter designed to be bidirectional?
This is Peter. I'll take that question. So as a general rule, inverters can be designed to be bidirectional by replacing all the diodes with active switches, such as MOSFETs or silicon carbide devices. And then having done that, we have total control over all of the switches. The central microcontroller then needs to have additional algorithms built into the firmware that are able to support the switching and PWM control for operation in each direction, which is going to be different in each case. It also needs to be able to detect where the power is being connected, either one side or the other side of the inverter, and to be able to operate in the correct mode to be able to support that. So it's basically a hardware and software answer to the question. Replace all the diodes with switches, and make sure that the control firmware can support the power conversion in each direction.
All right, thank you, Peter. We'll move on to another question here. Regarding the multimodular topology, do you also have solutions that come with the software?
Yes, this is Peter again. At the present time, we don't have a complete system solution for multi-module ESS. We do have suitable components such as MOSFETs in power packages, gate drivers, microcontrollers, and BMS controllers. We also have the technical expertise to be able to support our customers in the application, in the development. However, developing a solution with hardware and software is certainly possible, but we have to consider that the ESS module could be configured in different ways, so that there isn't just a one solution that everybody uses there. Everybody has a different, slightly different way of doing it, different configuration of the MOSFETs inside the module. And also there are a large number of modules in a system with a central controller that communicates with all of them to be able to create a fully operational system. So to come up with a solution that includes hardware and software would be quite challenging.
All right, thank you, Peter. Another question came in here. What makes silicon carbide devices of Infineon better than those of its competitors?
So Damian speaking again. We discussed already before about zero voltage gate driving. So I already partially mentioned before. So basically, Infineon silicon carbide MOSFET doesn't require any more negative voltage driving, what simplifies the customer design. And we see that some other competitors, since they have the issues with unwanted return on, they need negative voltage. And the Infineon silicon carbide MOSFET doesn't need any more. Thank you. That's
right.
The answer from my side.
All right. Thank you, Damian. We'll move on to another question here. And this one's, the wording's a little strange, but we'll work through it here. How is the multi-modular approach, in the multi-modular approach, will it be able to add up to 2 batteries of different SOH and chemical properties? Each kind of battery requires different charging topology, and how is this achieved?
Okay, this is Peter. I'll take that one. Oh, sorry,
Okay.
Ned, go ahead.
Okay, I will start, and if you want to add, you can add on this one, yeah. So answering this question, that's the beauty of this multi-modular approach, that you can use different batteries, different chemistries, because as you have seen in the slides before, each of these modules of these batteries has its own converter or power conversion. And this is not just function as a power conversion, but also kind of as, you can call it a BMS. It's a BMS for free, how we see it, because you can bypass these batteries when you charge it and discharge it, or while charging, for example, if you say there's a different SOC, yes, you just bypass this battery, and then you can just charge the other batteries that you have in this rack. So this is the beauty, I would say, of this second life of batteries, and this is why we also partnered up and trying to get this, I would say, innovative approach, because as also mentioned, there will be a bunch of EV batteries coming to the market, and we rather be sure how we can recycle and reuse them in a green way. So anything you want to add, Peter?
Only to say that the actual modules in the multi-modular systems are all the same, regardless of what type of battery is used. There are bidirectional DC-DC converter that is basically capable of working with any kind of battery module.
All right. Thank you, Peter. Thank you, Ninad. Looks like we have time for just one more question here, and then we'll have to wrap things up. Are new packages being developed to address power dissipation of silicon carbide components?
So yeah, Ninad here, I can take this as well. Yes, certainly there are new packages in the plan, on the roadmap. If you're eager to know what this is, we are happy to have this communication or exchange after this webinar, where we can also discuss with you for what you're needing it. But certainly new packages are on the way, because looking at the silicon carbide technology, which is enabling different approaches than to traditional, let's say, inverters, new packages are a must. Talking here about topside cooling, more of SMD packages, not always like going with TO247, for example, going to D square pack, or even putting more dies inside. So certainly new packages are on the horizon. But as I said, happy to share more directly with whoever asks asked this question.
All right. Well, that looks like all the time that we have for questions for today. I'd like to thank Nenad, Damian, and Peter for a great presentation and Q&A session. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, if we did not get to your individual question today, someone will get back to you after the program is over. And we'd like to thank you, our audience, for attending today's webinar, Energy Storage Systems, Silicon Carbide, Multi-Modular Approach, and BMS Tackle the Latest Trends, brought to you by Tech Online and Infineon. And this webinar is copyright 2020 by AspenCore. The presentation materials are owned by or copyright by Tech Online and Infineon, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests and Infineon, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.